Okay, let's get started. This is an important problem, an important proof, and an important exercise because in this short video I'd like to show you that if an infinite sequence is in the space LP0, then it is also an element in another space, vector space LP, if P is not lower than P0. So by this exercise, by this demonstration, we will say that we can move between vector spaces. And another interesting fact, namely, specifically, if an infinite sequence, if a point is in one specific space, vector space, then it might be in another vector space. Okay, so this is what we want to demonstrate today, and we will take two steps. The strategy. It is a very nice proof in which we take two steps. In the first step, we will use the basic fact from elementary analysis that this inequality holds for, and this is the point, for elements below 1, strictly below 1. These Xi elements are the elements of the infinite sequence X, and for the exponents, these exponents. Okay, this is the first step. And in the second step, we will show that if an infinite sequence is in the vector space LP0, then elements of this type, the number of elements of this type must be finite. So, specifically speaking, cardinality is finite. Okay, so this is our strategy to follow. So let's take the steps one by one. Step 1. Let me draw a figure. We will limit our attention to this open interval. It can be half open, actually. And let's take the powers of elements between 0 and 1. So let's have Ci here. This is the power of Ci when the exponent is 1, and by the strict convexity of the power function, we can see, oh, it's ugly, we can see that the higher P is, so to say, the more convex is the curve. So in general, we can say, on the basis of the basic characteristics of the power functions, we can say in general that this inequality holds for elements strictly below 1, for exponents like this. This is the point. This inequality is the point because from which it follows that the sum of these elements is in another inequality okay, and this sum must be finite. We know that this sum is finite as the infinite sequence is in LP0 by assumption. Okay. For elements, the absolute value of which is below 1. Okay. And here, if there is strict inequality here, then we have strict inequality in the sum as well. Okay. And this is still finite. Okay. For elements, the absolute value of which is below 1. Here, I like to make an important point. We mustn't say that an infinite sum is always finite when the absolute value of the elements is below 1. We mustn't say so. It would be a serious mistake. So it does not follow that an infinite sum of elements, the absolute value of which is below 1, the infinite sum is finite. This would be a serious mistake. All we can say is the conclusion that if an infinite sequence is in the space LP0, then its elements, the absolute value of which is below 1, they form an infinite sum which is finite with a higher exponent. So this is a much weaker claim. So what we have demonstrated that for an infinite sequence which is in LP0, its elements, the absolute value of which is strictly below 1, then their sum is gonna be finite. Okay, just because of the basic characteristics of the power function. However, the cardinality of these elements is uncertain. We don't need to be worried because this inequality holds even if the cardinality is infinite. So we are not in danger, so to say. So to learn more about the cardinality of elements of this type, we learned something about in step 2 to learn more about elements of this type. Okay, so we want to show that the number of elements of this type is finite. Okay, so let's see how to show this. Let's assume the contrary. Assume the contrary. The cardinality of elements of this type is infinite. So we have infinitely many elements of this type. And let's check if we get a contradiction. So let's assume the contrary. We have an infinite sequence written in this form. And this is in the space LP0, such that the number of elements of this type is infinite by assumption. Okay, let's create an index set. So we have the following set. In this index set, we collect the indices of those elements, the absolute value of which is equal to or higher than 1. We know that the cardinality is infinite. Yep. Because we assume, okay, I was just thinking for a moment. Because, yes, so here, okay, I was just confused. So here, at this point, we assumed that cardinality of the elements of this type is infinite. So from this, it follows that the cardinality of the index set is infinite. So we have infinitely many elements in this infinite sequence, the absolute value of which is equal to or higher than 1. Okay. If an element is equal to or higher than 1, it follows from the basic characteristics of the power function that this inequality holds for all I in this index set, also from the following from the basic characteristics of the power function. If we are in this zone, then it's obvious that if we have an element over 1, then its power is going to be higher than itself. So this is a basic fact, also following also from the basic characteristics of the power function. And from this, just like in the previous step, it follows that the sum of such elements cannot be lower than the simple sum of the elements. This is a fact. By assumption, note that by assumption, the number of elements in the sum on the right is infinite, because by assumption we have infinitely many elements, the absolute value of which is higher than 1. So let me summarize. We have infinitely many elements of this type by assumption. And from these elements, we can create partial sums. So for instance, Sn is the sum of the first n elements from the index set. Sm is the sum of the first m elements from this index set. So now we can create partial sums. Now that we have created these partial sums, we can be sure that this inequality holds for any n and m indices with this inequality, even if n is larger by 1 than m. Okay, so because of the absolute value of any element is equal to or greater than 1. So no matter how hard we try, we cannot create partial sums to which an inequality of this type held. So consequently, partial sums do not form a Cauchy sequence. Okay, why is it so important? Because a sequence is convergent only if it is Cauchy sequence. See page 33 of the Leuenberger textbook. So every convergent sequence must be Cauchy. Every convergent sequence is Cauchy. It means that the sequence of the partial sum is not convergent. Once again, the sequence of the partial sums is not convergent, so it must be divergent. So this is true. And if in the next step, if this inequality holds and we keep this assumption, then very importantly, this inequality holds following from the basic characteristics of the power function. So it's not finite. It's not finite. Consequently, x cannot be in the space LP0. So we receive the contradiction. We have received a contradiction if an infinite sequence is in the space LP0, then the number, this is important, then the number of elements of this type must be finite. Alright, because on the contrary, if it had an infinite number of such elements, it wouldn't be in space LP0. So now we are in the space LP0 and we have a finite number of elements of this type. So we have a finite number of these elements, and even if this inequality holds, again, also from the characteristics of the power function, the sum of the sum of a finite number of elements remains finite, so it doesn't endanger our membership in the LP or LP0 spaces. Let's demonstrate it formally. Okay, so even if we have this inequality, the sum is still finite. This is my claim, which we can prove informally, but we can do this. We can prove this informally, but we can do this formally too. So let's have a formal proof to see that the sum the sum of elements with indices from the index set is finite. Okay, so let's cut the sequence, the sum actually, into two parts. One part is the sum of elements from the index set. So just to be specific, these elements are equal to or higher than 1. And this is the other part of the sequence, with indices from the complement to the index set I. So these elements are strictly, their absolute values are strictly below 1. Okay. We know from the previous step that the cardinality of the index set is finite. Here we assumed that in the previous step we assumed that elements, the absolute value of which was equal to or higher than 1, so their cardinality was infinite, but we received a contradiction, so now we must assume that their cardinality is finite. Okay, so we identify the members in this sum, and we know that their index set is finite, and consequently their sum is also finite. Okay, so a finite sum of finite numbers is finite. Okay. All right. Now we can move forward and we can rewrite the sum as B plus the sum of elements, the absolute value of which is below 1, strictly below 1. Okay, and to this sum, it is true that if we increase the exponent, we receive a lower sum, just because of the basic characteristics of the power function that we have already used in the previous steps. If p is equal to or higher than p0, so the following inequality also holds. And as a last step, final step, please note it doesn't contain the sum of all CIs, only those the absolute value of which is below 1. So this inequality also holds because X is in the space LP0 by assumption. So what we have received is this sum is finite. Consequently, X is in the space LP if x is in LP0, and this is what we wanted to show. That's all for today.